Okay, the next chapter in our textbook is all about acids, bases, and salts. And there were two main theories developed in the late 1800s and early 1900s to explain acids and bases. So let's start with the earliest one, called the Arrhenius theory. This theory is far and away the oldest one, and it was developed in 1887. All right, and it's a pretty simple theory. And what he did was he broke things down into either acids or bases. So he called the acids Arrhenius acids, or I guess that's what we called them now. Back then he just called them acids. But it's any substance that produces protons or H plus ions when dissolved in water. Produces H plus ions when dissolved in water. Okay, and I'm going to put a little asterisk here next to the H plus. It's really not the case that we produce H plus ions, and he didn't know this at the time, but he was fairly convinced that we were producing H plus ions in water. But it's a little bit different than that. We'll talk about that in a second. And then obviously he came up with a competing theory to describe bases, and we just called these Arrhenius bases. And this is going to be any substance that produces hydroxide ions. And that's OH minus for hydroxide. Okay, so the main difference, as you can see, is acids produce H plus ions and bases produce hydroxide ions in water. So let's take a few examples here. Okay, in the first example, we've got HCl. That's hydrochloric acid. If this is in water, we would indicate this as being aqueous, which means it's going to split up into ions. And we'll get H plus ions, and we'll get Cl minus ions that will dissociate when dissolved in water. We could also have something like sodium hydroxide. Again, if we put this into water, it will completely dissociate into sodium cations, and this would be aqueous. And we would get hydroxide anions, again as aqueous. So the main idea here is this must be an acid on top because we're producing H plus, and this must be a base on bottom because we're producing OH minus. All right, but like I said, there was kind of a hiccup in this theory. He was convinced that it was H plus ions. The reality is we can't produce those ions in water, and this led to a later theory called the Bronsted-Lowry theory. And the Bronsted-Lowry theory basically got to this point where it said that H plus does not exist as a free ion in water. All right, it's a little bit weird to think about, but what I like to describe protons as, which is H plus right here, I like to describe them as a baton. So if you've ever seen a track relay and you see somebody hand a baton from one runner to another, imagine that baton is a proton. The proton has to be handed off from one person to the other. It doesn't just exist floating around in space on its own. All right, so this led to two new theories about acids and bases. So in this case, a Bronsted acid is going to be a substance that gives or hands off a proton. And again, a proton is just an H plus ion to another substance. So if we use that track relay analogy, the Bronsted acid is going to be the first runner with the baton. And then a Bronsted base is going to be the thing that receives it. Oops, I totally misspelled that. That receives a proton. All right, so this kind of is describing protons still, but it's just saying that they're handed off, they don't exist as free-floating or solvated ions. So let's take a few examples of this. Okay, and let's take water and hydrochloric acid, right? So I'm going to just draw these molecules out. So water down here is just going to be H2O. In fact, let me change the colors. Just say H2O. And we know H2O would be a liquid. And we're going to combine this with hydrochloric acid, which is HCl. So I'll put that up here. And I'll draw the full Lewis structure out. And then down below, I'll show the equation. And we're going to call this HCl aqueous because we know it's in water. Okay, when this happens, we're going to get a reaction to take place, right? So let's try to figure out what's going on. Well, hydrochloric acid, HCl, we can tell by the name is going to be an acid. So what it's going to do is it's going to give up this proton over here, right? So I've kind of put a red dashed line around it. And so when this happens, this oxygen on water is going to basically reach out and it's going to grab that proton, not the electrons, but only the hydrogen without electrons. Okay, and when that happens, these electrons that were right here, they're going to have to just hop over and live on the chlorine atom, right? So let's figure out what goes on. So when this happens, we form a new bond to that hydrogen, right? Whoops. Let's keep the color coding the same. So that hydrogen was essentially handed off right there. One of the lone pairs over here formed this new bond to that hydrogen. And then in addition, we're going to get our chlorine, but now it's going to have 4 lone pairs of sets around it. And again, one of those came from the covalent bond that was over here, right? Okay, but we're not quite done yet. We need to remember charges. If we look at the proton had a positive charge, which means that this oxygen must have a positive charge over here. So we put a positive. Conversely, the chlorine lost its positive charge, so it's going to be negative. So if we write this down as an equation, we would say H3O plus, and this would be aqueous, and then this would be Cl minus. Okay, so now we're on track. Let's go ahead and break this up. So over here, let's just focus on the HCl. It clearly gave its proton to something else. Okay, so let's just make a little chart down here. So it donated, let me get this with this bigger pen. It donated its H+, which means that HCl must be the acid, right? Right? Water, on the other hand, it took H+, which means it's acting as the base here. All right, but let's imagine what's going on this side of the equation. Well, what could act as the acid and do the reverse reaction? Well, in this case, the thing that now has the proton that could be given up is now the H3O+. So what we end up calling this is we call this our conjugate acid. And then over here, the chlorine would be our conjugate base, because in theory, right, we could imagine this reverse reaction where the chlorine takes this back and does the reverse reaction. Okay, so this is kind of a unique thing going on here. What we have is we've got a conjugate acid-base pair. And what I mean by that is this chunk right here and this chunk right here, they're related, right? So this would be a conjugate pair. All right, versus this And this right here, these two would be related as a separate conjugate pair. All right, let's do another example before we wrap up here, just because I know this can be a little confusing. Okay, and in this next example, again, I'm going to use water and draw the Lewis structure, but this time I'm going to use hydroxide over here, and the hydroxide has a negative charge, so I'll just put that little negative sign right there. And again, down below, I'll draw the molecular equation. So this is H2O liquid. We're going to combine this with OH minus aqueous. And we already know from the Arrhenius theory that this thing right here is going to act as a base, right? Because we said bases are things that produce hydroxide, right? So we could predict that, well, in this case, if this is a base over here, let me just write it down, that it will take or accept a proton from something else, right? Well, the something else is over here, which means it's going to take one of these. So we could imagine that it's just going to reach over, grab that proton, and then the electrons that were in this bond will just get nudged back onto that oxygen. So now we can show this full equation. And that just means that this right here will have an oxygen, but now the electrons from that covalent bond will be on that oxygen, resulting in a negative charge. And then over here, we would get a new bond formed to this hydrogen. Let me just put a circle around it. And that would occur with one of these lone pairs right here. So that lone pair would form a new bond. All right, so we could again rewrite this as OH minus aqueous plus H2O liquid. And you might be thinking, well, wait, aren't the starting materials and the products the same? Absolutely. So in this case, a better way of representing this would say that this is in equilibrium, right? So I'm trying to tie this back into this idea that not every reaction is a one-way arrow. In fact, a lot of reactions, including acid-base reactions, exist as equilibria. Okay, so now let's finish up classifying these. So over here, this gave up a proton. It donated it. So this would be our acid. And that means it donated its H+, right? And then if we think about the pairs, right? Well, over here, this was one group, and it's related to this over here. So if it was once an acid, that means on the right-hand side that it must be the conjugate base, because it no longer has its proton. In fact, it could take a proton back. And we could link these up as a conjugate pair. Okay, and then next, we've got these two that were related, right? Same parent molecules, just differing in the number of protons. That means that if it was a base over here, on the right-hand side, we would call this our conjugate acid. And they would be related as a conjugate pair. Okay, so before we finish up, I want to go back and compare and contrast these. So you see how in the top example, water acted as a base, right? But down here, water acted as an acid. Water is weird. Water can behave either as an acid or a base, and that's what I want to finish up talking about. And it's going to lead us into some more sections within this chapter. So water is weird. Let's put that in our notes. It can act as an acid or a base. It really just depends what the other component is in solution. So for example, with HCl, water acted as a base. But with sodium hydroxide, or just hydroxide I should say, water acted as an acid. All right, I hope that helps, but let me know if you have any questions.